Good morning. My name is Abdul Khali Mohammed, and welcome to Introduction to Medical Statistics. This is a brief overview of the topics that we'll be covering. Mind you, these topics we'll be covering are in no way exhaustive. There's a lot of material that could be covered, but we can't because we're limited with the time that we have. However, these topics would give you a solid foundation to build upon when you want to do independent research. So the first topics we'd be looking at would be study designs, population and sampling, sample size and precision, hypothesis testing, significance testing, p-values, confidence intervals, defining the data, summarizing the data both qualitatively and quantitatively, analysis of categorical data using chi-square test, analysis of quantitative data using unpaired t-test, and further topics for week 5. I would strongly recommend that you download the software R and R Studio before week 5. But in the last slide, you would actually see what the software is. So study designs fall under two broad categories in medical research. You have observational studies and experimental studies. So in observational studies, as the name alludes, you're not intervening in any particular kind of way. You're just observing the data as it is and making inferences from that data. In experimental studies, you would actually intervene by adding a treatment, and such. So for observational studies, we have cross-sectional studies, longitudinal studies, which would include cohort studies. Then you have case control studies as well. For experimental, you have randomized controlled trials and crossover designs. We'll be talking more about this in subsequent slides. Observational studies. These are studies where aspects of an existing medical process are observed. This could be based on clinical reports or surveys. We utilize statistical methodologies to interpret the possible causes of the observed phenomena. A classic example of this is John Snow, who is considered one of the founders of modern epidemiology and early germ theory, due to his work in tracing the source of cholera in Soho. So Soho is an area in London. And as you can see in the map that's attached there, you can see the very dark spot, the T in the center. Apparently there was a local tap there, and that was the source of the cholera outbreak. So in him mapping out the cases of cholera, he was able to figure out where the source of that disease was. And this is a classic example of an observational study. Experimental study design. So I would posit that this is one of significant importance to EFSTH as a teaching hospital. So experimental studies, these studies typically involve some intervention, such as giving a drug or a bed net to observe the effects of such an intervention on a disease. Most experiments are conducted in the lab on humans or animals, within a community or at hospitals. Subjects can either be diseased or healthy. All experiments on human subjects, however, are called clinical trials. So if the subject of the experiment is a human, it's called a clinical trial. In experimental studies, we utilize the principles of randomization so as not to introduce bias when allocating subjects to receive the intervention. Cross-sectional study is an is an example of an observational study. This is a study design in which the data is collected from numerous subjects within a limited time period. One of its advantages is that the results of them tend to be generalizable to a wider population. They are very economical and quick to implement, and it's very good at determining the prevalence of a disease. The cons, however, is that it might not properly reflect changes over time, and thus we can give a biased perception of prevalences or association, and it cannot be used to explain causation. But regarding the fact that it might not reflect changes over time, an example could be, imagine a cross-sectional study that was run in, let's say, in December at the peak of the malaria season, for example, in the Gambia. One might tend to think that we have very high prevalences of malaria, when in reality, if it was observed over the rest of the year, we'd understand that it's seasonal. So we have longitudinal study designs. Longitudinal studies examine the same subject over an extended period of time, and cohort studies fall under this study design. Its advantages is that it allows us to establish a current sequence of events. It also enables us to identify what the changes are over time. Also allows us insight into whether there is a cause-effect relationship. And a simple example of this is that you know malaria season comes after the rainy season. So if you've been observing people over an extended period of time, let's say 5, 10 years, for example, you would be able to notice that there would always be a peak in the prevalence of malaria shortly after a peak in the rains. The obvious disadvantages of this study is that it's more expensive and time consuming compared to other studies. And an example of this could be observing patients, OPD patients registered in the first week of January 2024, each week from that January to April, to the end of April, to investigate hemoglobin levels, for example. So some terminologies to consider. Um, the first one is randomization, which I can't really overemphasize how important it is to actually do randomization when you're doing experimental research. It reduces biases and it makes your analysis a lot simpler. And we would talk a little bit more about this further down. But it's fundamental in experimental research, particularly in clinical trials. It randomly assigns subjects to different groups and gives each subject an equal chance of being in any group. Some related aspects that come from randomization or lack of improper randomizations could be aspects on stratification. Stratification is where we know that, or we feel that we don't just simply randomizing might not produce balance in terms of certain groups. So an example of this could be that someone wants to run a study across the whole of the Gambia, and in that case, they they might employ stratification so that they could sample people to a reasonable degree from all the different administrative regions. Without stratification, we might get very few numbers, let's say in Lower River region by chance, right? Confounding is another aspect which I would have loved to delve deeper into. However, it's beyond the scope of this course, um, because it should be a topic in and of itself. But we would have practical experience of what confounding is in week 5 when we're doing the practicals. So confounding is a variable that's not the focus of the study, but is related to both outcome and the mean exposure. An example of this is, for example, we had a lung cancer study, and we're looking at the effect of smoking on lung cancer. In this study, age is a confounder because the older you are, the more likely you are to smoke. Children tend not to smoke. And the older you are, the more likely you might develop lung cancer, right? So age in this case is a confounder. It's related to both the outcome, which is lung cancer, and the exposure, which is smoking, but age is not really the focus of the study, but we just need to adjust for that effect. And then we have type 1 and type 2 errors. These would come up again in subsequent slides, but it's about false positives and false negatives. And it usually occurs when there's poor randomization. Not always, but sometimes it does. So population, in statistics, population can refer to any object or subject, does not necessarily people. It may or may not be limited to an area. Thus, a population could mean the total number of babies born at EFSDH or the total number of babies born around the world. So it could be something tangible, like the babies born in EFSDH, or it could be something abstract, the babies born globally, right? Target population, this is the population one wants to make inferences on based on the sample carefully collected from it. An example, if a vaccine trial was conducted on students that are typical of a community at large, we can make inferences about the whole community. Otherwise, we can only make inferences about the student of that community, right? So target populations are very important to identify, as it actually guides how you would go about sampling your data. So an example could be, let's say our target population is all women in the Gambia. It would be wrong for us to take a sample, for example, from just one area, let's say just from Banjul, women in Banjul, and then we say that, oh, that's representative of our target population. Since our target population is all women in the Gambia, it would be nice to have a bit more balance such that we've sampled women from Greater Banjul area or the regions in the country, right? Study population is the population from which we selected the sample from. It's not the target population, it's just the population that we selected our sample from. So let's say we wanted to make inferences about all the women in the Gambia, and we selected only women from Banjul. So our study population is women from Banjul. So if women from Banjul are similar to all women in the Gambia, then we can use that study population to make inferences about the target population, which is all women in the Gambia. But if it's the women in Banjul are atypical of all women in the country, we can only make uh, inferences about that particular study population, which is just the women in Banjul. Sampling. So a sample is the element of a larger population selected in a study. So like the units of that study. So this could be people, it could be households, it just depends on what it is that you're sampling. So that's it. The sample is not particularly of interest, but through it we can draw insights about the population. And I put this in red here because it's absolutely important. At least for the scope of this course, your samples must be independent. And when I say that your samples must be independent, for example, in a study where you're drawing blood from patients, if you draw blood from Adam, as an example, let's pick Adam, you can't say, okay, I'm going to draw blood from Adam and then the next day I'll draw blood from Adam again, or in the afternoon I'll draw blood from the same Adam, and now I have three samples. No, all those three samples really are just one sample. They're from Adama because Adama is the unit, right? It's not that we've drawn three times. It's more of where it came from, right? So it's absolutely important that your samples are independent. I'm not saying that you can have samples which are not independent, like you're drawing blood from Adama, but it requires a different kind of analysis that goes way beyond the scope of this course, right? And if you're thinking of doing a study like that, I recommend you talk to a statistician. Sampling is the process of selecting a sample from a population. Sampling variation means it's just referring to how when you're repeatedly sampling from the population, each person would have slightly different results. This is how I would summarize it. So I could give you a simple example where you're supposed to measure the height. I'm assuming that your class is about 40 or to 60 people. I'm not sure exactly, 60 doctors, sorry. I'm not exactly sure. But imagine I asked all of you to just pick a random sample of 5 people and calculate what their mean height was, right? You would all get slightly different results. That's an example of sampling variation. But the overall mean of your, let's say the overall mean height of your class is 170 centimeters. But someone would have 171, someone would have 175, someone would have 150. So that's an example of sampling variation, right? Sampling frame is all the possible elements of a study population from which you're sampling. And all elements of a sampling frame may or may not be known prior to study. So like for example, in the example that I gave about the class where you're trying to find the mean height of the students in your class, your sampling frame is actually all 40 or 60 of you. See, and your sample is actually just the 5 that you've selected to find the average height of. Methods of sampling. So to understand methods of sampling, it might be convenient to understand how non-random samples work and what they actually do. And I'm sure some of these methods you have used before. It's just to make sure that you understand what's actually happening when you use these methods, right? And this is not exhaustive. There are many more non-random sampling techniques. You have snowball sampling, amongst a myriad of others. So non-random sampling almost always lead to biases and may or may not be correctable during data analysis. Sometimes we do understand that it's more convenient to have a non-random sample, but you have to be able to account for that bias when you're doing your data analysis, and sometimes that's a nightmare, right? So it's better to always have a random sample. So the first one is convenient sampling or haphazard sampling. This involves little to no planning, and the units are selected at the ease of the researcher. So they just decides who's ever convenient that I pass by, I'll just try and sample them. But this makes a very big assumption that everyone in the population is the same, which is not the case. One easy way to illustrate a bias in this case is, for example, a male interviewer might select females, as opposed to males to interview. See? Another example is volunteer sampling. This is where all respondents are volunteers. This method is prone to something called selection bias, but is sometimes necessary for ethical concerns. So an example of this is, let's say, for example, you're running a study on a new drug and you want to test it on healthy individuals. So these healthy individuals have to be volunteers. You can't really force a random person in the population to come take your drug. No. And it's a new drug. You can't give this to someone who's already diseased and probably about to die, because you don't know what the effect of this drug is going to be. So you test it on healthy patients first, or healthy individuals first, and usually these people are volunteers. The other one is judgment sampling, and this is when the researcher feels that they understand the dynamics in the population, and they can decide who could be included and who can't. And as you can see, this is very prone to researcher bias, and sometimes it is worse than convenience sampling, right? The last one we talk about is quota sampling. This sampling is done until a specific number of elements are reached, and I know a lot of researchers do this. So one of these methods, of all the aforementioned methods, this one might actually be preferable, but it's also prone to selection biases, right? Methods of sampling, simple random sampling. So this method of sampling is ubiquitous. It's the most common, most widespread way of sampling. In fact, all other kinds of non-random sampling, right? All other kinds of random sampling depend on the concept of simple random sampling, right? So simple random sampling is the simplest random sampling technique, and aspects of it are utilized in part by all other forms of random sampling. This kind of sampling is typically done without replacement. So that means that once you've sampled a person from a population or an element from a population, that's it. You can't reuse that element again. Yes. Simple random sampling is implemented by obtaining a sampling frame. This is usually a list of the study population, and selecting a random sampling by two methods. One can assign sequential IDs for all elements and use a random number table to pick samples, or do this on a computer. My advice is do this on a computer, right? For this method to produce reasonably unbiased estimate, the sampling fraction actually, which is small n all over n, must be small. That's less than 10. As the sample size increases, this means that your sampling fraction has increased. The proportion that you're taking from the overall population is larger. You need something called a finite population correction, right? This allows certain biases to be weighted off. Another method of sampling is stratified sampling, and similar to when we were discussing stratification earlier, simple random sampling assumes that the population is a single entity, right? However, we know that populations can be subdivided. An example can be using simple random sampling by administrative region to get more representative samples from a small survey. The administrative areas in this case are considered subpopulations and are called strata. One could utilize this method if one fears that a particular stratum might be underrepresented or missed completely without stratification. There are several technicalities that one has to consider when using stratification. During data analysis, associations of two variables and other differences across each stratum might be influenced by stratification. And this can also influence your standard errors. We will talk more about standard errors in subsequent. Cluster sampling is a specific kind of multi-stage sampling. So multi-stage sampling means you'd be sampling from different hierarchies. So like sampling from compounds to households, that kind of mechanism. So it's a specific kind of multi-stage sampling where there could be primary, secondary, or even tertiary sampling in it. For cluster sampling, all elements of a cluster are sampled after doing simple random sampling on the clusters. An example is our primary is if our primary sample units are schools. Once we have selected a sample of schools using simple random sampling, we select all the children in each sampled school. There is generally a lack of precision with estimates obtained from this method. Sampling more primaries, however, when we sample more of the primary sample unit, it tends to increase that precision. This might prove more expensive, but it saves a lot of field work, because imagine now you don't need to sample 100 different schools. For example, you could sample 100 different schools, and maybe let's say you're just sampling 10 students from each school. But in this method, you can maybe sample, I don't know, 15 different schools, 20 different schools, but you're sampling all the students within those schools. See, so in terms of logistics, it might be cheaper. My humble advice is that if you're employing or trying to do a study where you would need any other form of sampling besides simple random sampling, talk to a statistician, right? Talk to a statistician. So in summary, simple random sampling is the most prevalent form of sampling in scientific research, and elements of it are used in various other kinds of random sampling. Stratification tends to overestimate the variation, so you get a bigger confidence interval, which we'll be talking about in subsequent slides. Cluster sampling tends to underestimate the variation, so your estimate seems to be overly precise. But please, I reiterate, consult a statistician when you're thinking of designing a study. We can help you when it comes to areas of sampling and sample size calculations. Right. We would still talk about sample size calculations to an extent, but first we would just talk about sample size. So typically our main objective in research is to find an adequate sample size to test for a clinically important difference and have a good chance of finding a statistically significant difference. For this, we need a good sample size, a clear hypothesis, and adequate power. Sample size calculations give us an estimate of the number of units we need to sample to make useful estimates about the population. Large samples do not correct the bias caused by poor sampling strategy. That's something that a lot of people tend to think, that if you just have more people, you have a very bad sampling strategy, but if you have more people, then your sampling should be fine. That's wrong. Sample size formula assumes simple random sampling, and adjustment needs to be made for different sampling strategies. Sample sizes can only be obtained using simulations for some types of data, right? Some kinds of data can't really use a formula to calculate the sample size. You have to simulate the data, right? So we talk briefly about precision. So you would notice earlier I mentioned something like confidence interval. Confidence intervals are a measure of precision, right? So sample sizes essentially allow us to improve precision in our estimates. The larger the sample size, the more precise our estimates, right? Confidence interval, this is an interval within which we expect to contain the population parameter. So the population parameter could be, let's say, the mean height of men in the Gambia. That's the population parameter. But we selected a sample from, people who visited Banjul Hospital, EFSDH Hospital, and we got our point estimate, our mean, from those samples, and our confidence interval. So that confidence interval is a measure of how likely it is to contain the true population parameter. Though the simplest way to explain this is if you look at the the graph at the bottom, the one with the horizontal lines with the red line peeking out there, that's an example of what a 95% confidence interval looks like. What this means is that the individual lines are individual studies, right? So let's say we were looking at the mean height of all men in the Gambia. That dotted line that goes vertically, let's assume that that's the mean height of all men in the Gambia, right? I know it's talking about apples, but let's assume that that's the case. Now, the horizontal lines, these are the individual samples. So let's say we have 20 students in the class. Each of you decides to run a study to find out what the mean height of men are in the country. So those horizontal lines, those are examples of what you found to be the mean and your confidence interval. So that line, the width of that line is your confidence interval, for example. Now the red one that's blinking, that's outside, it doesn't cover the mean dotted line, which is vertical. That is an example of what a 95% confidence interval does. 5% of the time, the confidence interval that you've calculated from your sample won't actually contain the true population parameter, right? So confidence intervals are a measure of precision. The larger your sample size, the smaller your confidence interval, right? And we'd be detailing this a little bit more in subsequent slides. Also note that for z-test, any values in the direction of the red arrows are considered statistically significant. So this bell-shaped curve that you can see here, this is absolutely important that you understand it and you understand what's happening here. And when we go to testing for quantitative data, this becomes very important, right? So the way that this bell-shaped curve is, you can see it says that 95.5% of the data is in between minus 2 SD and plus 2 SD. So the minus 2 SD and plus 2 SD, SDs here are the standard deviations. They are a measure of variation from the mean. Now, in hypothesis testing, we'd be looking at testing at the 5% level, or we can talk about it in terms of 95% confidence interval. Anything that goes past this 2 standard deviations, and it's not exactly 2 standard deviations, it's 1.96 standard deviations, and you can remember that number 1.96 because it would come up later on. Anything that goes past those values, so 3 standard deviations or negative 3 standard deviations, those are they're significant at the 5% level, right? So just remember that. Okay, hypothesis testing. So let us assume that we're comparing the proportion of hemophilic women, comparing two groups where one received a new drug and the other received a placebo. We can test to see if the proportion of hemophilic women is significantly different between the groups. We can do this by comparing the proportions directly or by comparing the difference in proportions between the groups if that proportion is different from 0, right? When we test this hypothesis, there are 2 errors that can give us false conclusions, and it's important to understand this. For hypothesis testing in categorical, in this case binary data, we need a base level of comparison. So in this case, we can say, because we have a new drug and a placebo, we can use the placebo as a base level of comparison to see the effect of this new drug, whether it's going to increase the proportion of hemophilic women or reduce it. Also, we need an effect size. So in this case, because it wasn't really specified, we have an effect size which would be comparing against 0, and that's the difference in proportions between the 2 groups. So that's an example of an effect size. we could have also said that the difference in proportions is 10%. That's also an effect size, right? So in hypothesis testing, one must always test against a null hypothesis, right? H naught. In our previous example, we can see that the difference in proportions between the treatment groups is D, if we assume that that's it. Then our null hypothesis, which is H naught, is that D is equal to 0, right? Whatever difference we find in proportions is equal to 0. Then our alternative hypothesis is that, okay, D is not equal to 0. We don't know whether D is bigger than 0 or whether D is smaller than 0, but D is not equal to 0. So let us assume, in this case, that D is equal to 0.001. It's a very small number. Now, for significance testing, what we try to do is to find out how significant this difference is from 0, right? And when you're doing significance testing, you have you can potentially run into two errors, right? The first error is the type 1 error. This is where you reject the null hypothesis when it's true. And in this case, our null hypothesis is that the difference in proportions is equal to 0, right? So we reject the null hypothesis. We're saying that, oh, there is a difference in proportions, but the reality of the matter is that no, actually, there's no difference in proportion, right? The second error, which is a type 2 error, is we fail to reject the null hypothesis when it's false. And in this case, what this means is that there is actually a difference between the two proportions. However, we couldn't find enough evidence to reject the null hypothesis that, oh yeah, there is a difference between the two groups, right? So in this case, it's like we're having a false negative, right? So to better understand these kinds of errors and how they are related to statistical power, um, type 1 error, this is the significance level. So, when you're creating a sample or you're doing a sample size calculation, they usually ask you for a significance level. It's usually 5%. When we're doing statistical testing, we test against, a 5% significance level. So it's that significance level, that's that alpha that you can see inside the table that's there. So commonly, this is 5%, which is called 95% confidence. That's the way to think about it. Type 2 error is 1 minus the error, which is type 2 error. 1 minus this error, type 2 error, is the statistical power of your study. So typically, you have errors of 10 to 20%. Um, so statistical power usually ranges from 80 to 90%. You do have studies that have below 80% sometimes, but most of the time we would assume that that study is underpowered. They're not really powered very well, right? So spend a few minutes to understand these concepts. However, we would be doing some practicals and sample size calculations next week, from which you might be able to better understand it. But spend a few minutes with this table and understand it adequately. It's advisable. So significance testing, and here we're talking specifically about z-test. Now, don't let the term z-test frustrate you. If it's new to you, don't let it scare you. There are different kinds of testing in statistics. You have things like f-test, you have t-test, you have z-test, you have chi-square test. These are all different kinds of testing in statistics. But for the purpose of this example that I'm about to give, we're assuming that it's a z-test, right? And the z-test is the most widespread test statistic that we have in statistics. So it's quite ubiquitous. You'd be seeing it often, right? So significance testing seeks to quantify just how likely it is that we are observing our effect size should the null hypothesis be true. To help understand this concept of significance testing, let us use an example, right? So in a COVID-19 trial, we investigated the difference in mortality. The difference in mortality is 5%, right? Amongst new patients, and we have 100 new patients who received a new drug. So amongst those who received this new drug, 10% of them died. That 10% P1 that's there is about mortality, 10% mortality, right? Then versus another 50 patients, which is N2, who got a placebo. So amongst those who received the placebo, 15% of them died, right? So you know that difference in mortality that we were talking about at the start, which is 5%, is just the difference between the 15% and the 10%, right? That's all that is, right? So in this example, our hypothesis is that there's no difference in mortality between the two treatment groups. In order for us to test the significance of this, we need to first calculate the standard error. Now, the standard error for a difference in proportions is that. That's that formula down there. Now, you don't need to cram this formula. This formula also changes if you, let's say you were finding the standard error for a difference in means, for example. It would be different. So the general framework is the same. You could understand the general framework of the formula, but I don't think that you need to cram this. This is only a statistician who would be expected to know this, right? So don't worry about that. So the standard error of the difference in proportions is 0.0587. This is the result of plugging in those numbers, the 100 patients who had a 10% mortality rate and the 50 patients who had a 15% mortality rate. This is the result of plugging those numbers into that scary looking formula in the previous slide, right? So I'm not expecting you to calculate it yourselves. The result is there. Now, to, to test for the significance, this is what the z-test is all about. The z-test produces a z-statistic, see? And it's basically the observed difference minus the null hypothesis divided by the standard error of the difference, right? So because we calculated a difference, the null hypothesis that the difference is 0, right? And the alternative is that the difference is not equal to 0. So in our case, when we plug in those numbers to the formula, we have z is equal to 5% minus 0 divided by 0.087. 0.0587, sorry. And we have a value of 85. Now this observed difference is over 85 standard deviations from the null hypothesis. Think about it this way. You remember the precision when we were looking at the normal distribution, when we were talking about precision, and I mentioned that any value that exceeds plus 2 standard deviations or 1.96 plus 1.96, and any value that's below minus 1.96 is considered statistically significant at the 5% level. That's what this is. So 85 is way above 2, which means that this is very significant. So there is a very significant difference in mortality rates amongst these patients. So the new drug, right, so I mean the p-value in this case is something that you could calculate manually if you wanted. However, I would advise you against it. This is something that we tend to do when we're learning statistics. But if you're an adventurous person, you can. I would welcome you to try. Um, so the question here, this is your first among several questions. I would advise you to try and attempt them. This is a way of you assessing yourself. And we're not grading you on it or anything like that. It's just a way for you to test whether you are really understanding these concepts or not. So, what would you conclude from this study, given this result, on the effects of the new drug as it relates to COVID-19 mortality, right? So, after obtaining our test statistic, which was that Z value, which was 85 point something that we had in the previous slide, we use this to help us declare whether the difference in proportion is statistically significant at the 5% level or not. In our case, the p-value is less than 0.01. Hence, we reject the null hypothesis in favor of the alternative, which is that there is a difference in mortality between the treatment groups, right? So this also kind of answers part of question 1 asked on the previous slide. The other thing that I would point out is that p-values are never zero. So sometimes you run things on a software and you get a p is equal to 0.000. P-values are never zero. So you always put it as less than something in that case, like less than 0.001, less than 0.00001 if you want to, as long as it applies, right? But as it's stated here, less than 0.001, it's appropriate, right? Do not look at the 5% threshold as a hard boundary. So a lot of people tend to do this. They might get a p-value of, let's say, 0.06, and then they conclude, oh, we reject the null we fail to reject the null hypothesis because it's not less than 0.05. No, I mean the 5% threshold is not like a hard boundary. We would advise that anything that's below 0.01, you consider it as some evidence of an association of any kind, right? So some weak evidence to reject the null hypothesis between 0.05 and less than 0.1. See? So that's just something to note. And also, people tend to overly focus on p-values, and sometimes it annoys us statisticians because you could find something that is clinically relevant, but because it's not statistically significant, a researcher might be less inclined to publish it. We say publish it, right? So imagine, for example, if our new drug reduced mortality by 60%, but we have a p-value of 0.28, which is not significant at the 5% level. It's not even close to significant. And we just conclude, oh, there's no effect. We fail to reject the null hypothesis, so there's no effect. No. This shows some clinical relevance. You have a drug that's able to reduce mortality by 60%. So one of the things that could be done to make this study statistically significant, if that the effect of the drug really is that it reduces the mortality by 60%, and that's really what the drug does, then to improve the p-value, what one could do is you increase the sample size. When you increase the sample size, you get greater precision. With greater precision, your p-values become lower, right? So the next slide is about confidence intervals, which gives us an estimate of how precise our point estimates are. One thing that I think is important for you to note is that the last couple of slides where I've been talking about hypothesis testing, significance testing especially, and p-values, All of these are linked with the confidence intervals. They're all linked, right? And these concepts, they're quite common in all aspects of inferential statistics. We'll be talking about significance testing, confidence intervals. You would see them all the time, right? So within the same experiment, let's say we were calculating the mean height of people in the class, and at the start I asked you to pick 5 students. Now imagine I asked you to pick let's say 35 students instead of 5. As your sample size increases, your confidence intervals become smaller, right? And because the way that your confidence intervals become smaller is because your standard error decreases, right? And the p-value becomes smaller. The general formula for confidence interval, and in this case, let's say 95% confidence interval, is x bar would be the sample mean plus or minus 1.96 times the standard error. The 1.96 is not just an arbitrary number that I picked up from my head. If you remember when we were talking about precision and I mentioned the bell-shaped curve, 1.96 is the cutoff that, so it's minus 1.96 to 1.96. Within those two cutoffs is where 95% of the data in that bell curve falls under. That's why it's called a 95% confidence interval. So above 1.96 you have 2.5% of the rest of the data, and below minus 1.96 you have 2.5% of the rest of the data, right? And that's your significance level. The combination of that is 5%, right? The standard error in this case, in a pragmatic way, you could just define it as the square root of the variance all over n. You could also consider it as the standard deviation divided by the square root of n. And n is the number of samples that you've had, the number of observations in your sample, right? Now, what you would notice is that it's because since the variance is divided by n, as n increases, your standard error would decrease. So as your standard error decreases, your sample size becomes smaller. Your confidence interval becomes smaller because that expression 1.96 times the standard error becomes smaller, so your confidence interval becomes narrower, right? And as your confidence interval becomes narrower, your p-value would decrease. It would decrease. So now let's do a bit of defining types of data that you have. I am sure you must have encountered qualitative and quantitative type data with Efwa when she was going through her lectures with you. So I would say that in statistics, in summary, we have two types of data in general, qualitative and quantitative. The qualitative data types, they tend to not be numeric, so they are non-numeric data, and they're supposed to illustrate different categories of things. For example, sex, male or female, ethnicity, blood group, level of schooling, those kinds of variables. Those are all, you could consider them qualitative data. And to be more specific about them, these are variables that you would call categorical data. So like sex could be considered a categorical data, but more specifically, it's a binary data because it's one or the other. You can term it as a binary data. Actually, not necessarily binary data. Let's say we were looking at whether someone is female, so the opposite is if they're male. So when we're looking at someone is female, that we can create a derived variable which is binary, where it's 1 for female and 0 for male, for example. Then you have ordinal data. Now in ordinal data, there seems to be some sort of order in your categories, right? So you could have something like high, high, highest. That is a form of, it escalates or it decreases. That's a form of ordinal data. I think in clinical research, an example of ordinal data is if a respondent is asked how are they feeling? Are they feeling good, you know, okay, bad, things like that. So that's an example of an ordinal type data. Nominal data is one where the categories, they have no order to them. Like ethnicity, for example, there's no order to them. That's nominal data. So all these categories we can assign numeric indicators for when we're doing analysis, right? So we can say, let's say Mandinka is 1, Fula is 2, Wolof is 3, Bambara is 5. We can do things like that, even though they're text, it's categorical data, like it's text. We can assign numeric indicators for them when we're doing analysis. The other kind of data, which is one we would be working on mostly, is quantitative data. Now, these variables are numeric and are typically from counts or measurements, such as the number of subjects in a household and the height of subjects, for example. These variables can also be rates, so you're measuring something over time. So let's say the number of people that sit at a bus stop over an hour, for example. You also have other kinds of data, like quantitative data, where you actually need to transform the data. So when you're doing quantitative data analysis, it's best that your data looks normally distributed, like that bell-shaped curve. It's better that it looks that way when you're doing an analysis. So if it's not, sometimes you might have to transform it to look that way. So like an example in this case is a log transformation to make the data look normal. Another one is a derived variable, for example, growth rates. These are sort of formulas that are, for example, growth rates, they are formulas that are devised by the WHO and the CDC sometimes, and they allow us to input some values and we get derived values from them, like Z-scores, for example. So the data from the quantitative data, it could be either discrete, like integers, like age in years, for example, or it could be continuous, where you're measuring age with all the decimal points after it. So in order to also understand the type of nomenclature or words we use, it's important to distinguish what is your outcome from your exposure, right? As researchers, we not only have to identify the appropriate data display or statistical method to use, but it's also crucial to distinguish between our outcome and our exposure variables. So the outcome variable, this is the variable of interest whose occurrence or variation we want to understand. This is usually dictated by the research question we seek to answer. An example of this is if we were trying to look at lung cancer patients, the outcome variable in this case would be whether you're positive for lung cancer or not, whether you have lung cancer or not, right? Um, the exposure variable in this case is one that influences the size or the occurrence of the outcome variable. And in the lung cancer example, smoking could be the exposure. See, smoking influences whether someone has lung cancer or not. So we're trying to map the effect between the exposure and the outcome, which is whether smoking causes lung cancer. Right? Please note that the context of the study can cause a variation in these terminologies. Right? For example, in a clinical trial, the exposure is usually called a treatment group. Like, you know, in a case control study, the outcome is the case control status itself, right? So the outcome is the case and the case controls are whether they are positive or negative, right? And finally, in this last study, the exposure variables are called risk factors. So continuing and summarizing data, when we have qualitative or categorical data in this case, it's relatively straightforward to summarize categorical data. Just count the number of observations in the category. Presenting these counts in a graphical format is what we call frequency distribution. Um, Example, using data of patient categories at a hospital testing for COVID-19. You can see in the table we have um, clients, then we have the demo group, which group they belong in, the frequency and the percentages, right? So we have the clients, the miscellaneous adults, the other adults, the patients, and the unidentified. And you can see the associated numbers with all of them and percentages with all of them. And in the graph below, it just represents a bar graph. It represents the table above, right? Similarly, when we're summarizing quantitative data, um, you can see we employ a similar mechanism, but in this case, we use something called a histogram. Now, a histogram is not so dissimilar from a bar plot. The bar plot is that um, everything is disjointed in the x-axis, whilst in the histogram, everything is connected, really, right? And we can also present it as either frequencies, which is counts, or percentages, right? Histograms can be plotted as frequency polygons as well. This shows the distribution of data by connecting the midpoints of each of those bars, right? Displaying continuous data as a histogram is crucial in planning which statistical methodology you're going to use, whether transformations would be adequate, and it can allow you to notice outliers. So as you can see in the histogram we have here, circled around the 500 mark, those two observations, and even the one around zero, they could be potential outliers. They might not necessarily be outright outliers, but we should consider them carefully, right? And the way that we handle outliers sometimes is that we remove them from the analysis if it doesn't make sense. So imagine, for example, you were running a study on hemoglobin level and you had a patient who had a hemoglobin level of 150, when in reality, it couldn't go past 15, for example. The one that's 150, you would definitely exclude from your analysis, right? You wouldn't include that person in your analysis, you delete them. So that's the simplest way to handle an outlier. But don't go deleting willy-nilly, right? It might be important. It might be genuine data, and it might also be good if you just consult with a statistician before deleting outliers. So in the graphs below, it shows about skewness of data. So the one in the center, which is the normal one, that's the normal standard curve. This is like the bell curve that we were talking about when we were talking about precision. If you look at the histogram above it, yeah, it is somewhat similar to the one in the center, right? But one could also argue that it looks a bit skewed to the right, right? Positively skewed. So, you know, these skewness, they have an impact on what you can do with your analysis. If you look at the one in the center, you have mean, mode, and median. all on the same line in the center, right? If you have the mean below the median and the median below the mode, then you know that you're negatively skewed. If you have the mode above the mean and the median and the mean, then you know that you're positively skewed. So measures of central value. Now that we've looked at graphical ways of illustrating data, we need to consider numeric ways of summarizing quantitative data. There are numerous ways of summarizing quantitative data. However, for this course, we would limit it to the following: median, arithmetic mean, geometric mean. And there's an explanation on when to use which. So in your first example, we'd be considering the median as a measure of central value, or we could sometimes call it central tendency, right? So if you remember the graphs under the histogram, you know, the one in the center where we had all mean, mode, and median at the center, that's what we're trying to do. We're trying to find the center of that distribution. And when you consider that with what we've understood about confidence intervals, you know, if you have the mean at the center of a normal distribution, then you can have plus or minus 1.96, and it's representative of your actual data. If there's skewness, then you can't really do that, because plus or minus 1.96 would look different on the right to on the left. So if it's positively skewed, you know, plus or minus 1.96 will be different on the right compared to the left, right? So, so median in this case, this is the value that divides the distribution of the ordered observations in half, such that 50% of the observations lie below and 50% lie above. In the special case where two terms are in the middle, we find the average of the two terms, right? So it's very important that when you're given numbers, when you're to calculate the median, you have to order it from the smallest number to the largest number before you calculate the median. Very important, right? So this is your first exercise. Also, it's not assessed. There will be more subsequently. Just have a look at it, test your understanding of it, and this way, when we, or if we have an interactive session, you might be able to ask if something is bothering you about certain concepts when it comes to these things. You can ask such questions. So medians tend to be used when there is skewness in the data that cannot be easily transformed. Also when there are outliers, also when there are very few observations. So a rule of thumb is if you have less than 20, it's not a hard rule, you know, well, a rule of thumb is, you know, if you have 20, less than 20. So the next measure of central tendency is the arithmetic mean. Now, the arithmetic mean is the most commonly used measure of central value. It is calculated as the sum of the total number of observations divided by the number of observations. So that's the general expression. You're just adding up everything and you're dividing by the total number of units you have. So in this exercise, you're supposed to, it's the same set of numbers, you're just going to calculate the arithmetic mean of the same set of numbers. Arithmetic mean should only be used on data that has a normal distributed histogram, right? It's advisable, really. I think only is a hard word. It's advisable to use it on that kind of data. It may also be used in the case where a transformation can produce normally transformed data. So maybe you log transform your data and it looks like a nice bell curve, then you can use arithmetic mean. But that's actually a special case, which is what we call a geometric mean. So geometric mean uses the same concept as arithmetic mean. It's just that every observation is transformed. So in this case, we're using natural logs. We've transformed all our observations using natural logs, and we find the mean of all the observations using natural logs, and then we exponentiate that mean. That's the expression right there. right? So for the same set of numbers, calculate the geometric mean. That's your third exercise. Geometric mean should only be used on data that has a positive skew. So when it's negatively skewed, you can't use geometric mean, right? You'd have to consider other things. But when it's positively skewed, there is a possibility that you can use geometric mean. But always transform your data first and check to see if it's normally distributed, like the log transform data is normally distributed. So question 3, what does it mean when the arithmetic mean differs from the geometric mean, and which one would you trust over the other? In this case, what are the merits of the mean, the median, and the mean and the median as a measure of central tendency? So what are the merits of them, right? So another aspect in summarizing data is summarizing the variation. So, you've calculated your mean, you just get one value. It seems like you're wasting all of the other values that are in the distribution that you had. So what are the measures of central tendency? So measuring central tendency is important. However, we need to understand the spread of the data as well. So these are ways of measuring data spread. Oh, yeah. So the interquartile range, when we summarize data using medians as a measure of central tendency, we usually summarize variation as a measure uh, of where 50% of the data falls. This 50% is what is called the interquartile range. So it's the data that lies between the 25th percentile and the 75th percentile. The range is the interval between the minimum and the maximum values. So the range is not very informative because, like, imagine if you had values, the minimum of which starts from 0 and the maximum goes to 20, and values where the minimum starts from 100 and the maximum goes to 120, both of them would have a range of 20, but it doesn't really tell you much about the distribution that it's from, right? So that's why the range is not really a very good measure of variation. And what you would notice between the interquartile range and the range is that both of them only use two values. Of all the observations that you have, they only use two values: the 25th percentile or the 75th percentile, or the minimum value or the maximum value. That's the only two, and they just waste all the other values, right? So finally, we look at standard deviations and variance. Standard deviation measures the spread around the mean. Standard deviation is the square root of the variance. The variance is calculated as the sum of the square of the differences between each observation and the sample mean, divided by the total number of observations minus 1. So the formula is shown below, right? This is a more robust way of measuring spread because it actually utilizes all the different observations in your data. So these are just some exercises. I would advise you to do them. Um, so what are the interquartile range, standard deviation, and variance of the hemoglobin levels of pregnant women? What are the combinations of these? And which one would you use and why? So now we've come to testing. So this is like chi-square test. This is one of the more common tests that you would be doing when you're analyzing for associations in categorical data, right? So this is before when we were talking about probabilities and testing for them, we were looking at them in terms of just one variable, perhaps where we utilize only one categorical variable, and we were uh, checking to see if there's a difference in certain means between a particular categorical variable. But in this case, we're trying to test the association between two categorical variables, right? So, and for this example, I've restricted it to only a 2 by 2 table. However, you can do this for a 3 by 2, 2 by 3, 3 by 3. Really, as long as they're both categorical variables, you can do a chi-square test of association, right? So for this, we would create a 2 by 2 table and investigate whether the values of one variable differs according to the values of another variable, right? So let us consider an example to explain this. In a recent EFSTH neoplasm clinic, we observed that in May 2024, there were a total of 100 patients, 30 of which were male. Overall, we had 50 cases of breast cancer, of which only 5 were male, right? So this is just a description of the data. When you're doing a practical on this, you would see the data in its sort of holistic form, where you have probably a categorical variable that says whether someone is male or female, and another categorical variable that says whether someone is positive or they have breast cancer or not, right? So the information from the previous slide is what is summarized in this table. Uh, Remember, we said that we had 30 male patients. So if you look at the male column, there are 5 plus 25, which is 30 males. Then for the females, which would be 70, because we have a total of 100 patients, it's 45 plus 25, which is 70. In terms of breast cancer, we have 50 positive breast cancer patients. So you would notice that's 5 plus 45. Those are the 50 that are positive for breast cancer. Now I've color coded these, right? The black one is what's observed. That's what the data is. That's what we've observed. The blue ones is what we expect to be in that cell if there was no association between sex and breast cancer, right? If there was no association between sex and breast cancer, we expected 15 males to be positive for breast cancer, 15 males to be negative for breast cancer, 35 females to be positive for breast cancer, 35 females to be negative for breast cancer. And the way you calculate this is simple, really. The expected value is the row total times the column total divided by the total. So let's say for males that are positive for breast cancer, the row total is 5 plus 45, which is 50. Then the column total is 5 plus 25, which is 30. So it's 50 times 30 divided by 100. That's 15, right? That's how that 15 value, the blue in the cell, that's how we got that 15 value, right? So all the other cells is the same way. So like for females that are positive for breast cancer is 5 plus 45, which is 50, times 45 plus 25, which is 70, divided by 100, which is 35, right? So to get the chi-square statistic that's required for this test of association, the formula is given. It's the summation of the observed value minus the expected value, all squared, divided by the expected value, right? So in this case, our chi-square statistic is 19.05. Similar to when we had the normal distribution, there's a chi-square table that you could use. Now, for the chi-square table, the significance threshold at the 5% level is approximately 4. It's not exactly 4, it's like 3.8, right? It is essentially 1.96 times 1.96, because the chi-square is actually a combination of two standard normal distributions. You multiply them together, that's what gives you a chi-square, right? So that 1.96, which was the significant threshold at the 5% level, you multiply it with itself, you get about 3.8. That's the significance cutoff. And what you notice in this case is that 19.05 is way higher than 4 or 3.8. So we conclude that there is strong evidence of an association between sex and breast cancer, right? This method can only be used to test for association, but not test the magnitude of that association. We can't say, how, let's say, 50% more of males get breast cancer than females. No, we can't do that. We just know that, for example, there is an association. So one of the sexes tends to get breast cancer more than the other sexes, right? To test for associations, to test for magnitudes of associations, you usually do this through regression. And in this specific case, we would use logistic regression, right? So for your sixth question, which sex would you say is more at risk of developing breast cancer based on the two-way table, right? So now we come to the analysis of quantitative data. For quantitative data, it involves, in this case, we're just looking at a t-test. It's one of the simplest tests out there, and we're looking at an unpaired t-test. So there are two types of t-tests. You have a paired t-test and an unpaired t-test. So I'll just clarify so that you'd understand. For the unpaired t-test, you're testing two different samples that are independent of each other, right? But that's for an unpaired t-test. You're testing two independent samples which are different from each other. For a paired t-test, you're testing two samples from the same individual. So let's say you measure individual A today, then you measure individual A the next day after they have taken some treatment. That's a paired t-test, right? It's not an independent t-test anymore. It's a paired t-test. So you'd have to watch out for that. But we do a bit of that during the practicals, right? So for continuous data, we tend to compare means. We could compare medians. However, the gold standard when it comes to inferential statistics is to compare means, right? This would be after checking the distribution of the observations are normally distributed, right? So this is something, at least for this level, is acceptable. But what tends to happen is what we want is the distribution of the errors as normally distributed. Or then when we talk about the errors, you'd see that when we do regression, the distribution of the error should be normally distributed. So even if the variable, that you started with wasn't normally distributed at the start, it's still fine to use a regression if your errors are normally distributed. So for this, let's just consider this example where we're looking at birth weights, and the birth weights are in grams between group A and group B mothers. Now, what is the difference in birth weight and the 95% confidence interval? This is typically what we tend to calculate when we have data like this. So to do a t-test, we employ a similar procedure to when we were discussing hypothesis testing earlier. So since we've already been given the means, we start off by calculating the standard errors. Remember, the standard error is the standard deviation divided by the root of the number of observations, or you could just say it's just the square root of the variance divided by the number of observations. So what you would notice here is, since in the previous table we were given the standard deviations, we squared the standard deviation. So you could see in the formula that's written there is the square root of 150 squared divided by 100, which is the number of observations, plus 60 squared divided by 100, which is also the standard deviation for group B. And after calculating that, we get a standard error of approximately 16.16. For a large sample, and you could consider this a large sample, we have about 200 patients, 200 observations, independent observations. The confidence interval is calculated using the difference in means plus or minus the z value times the standard error. So as you can see here, it's broken down in a nicer way, where you have the difference in means minus the z value, which is typically 1.96 times the standard error, to the difference in means plus 1.96 times the standard error. So our difference in means is 300 grams. For the z values, there are two. Remember, we have one at the 2.5 percentile and the 97.5 percentile. Since this is positive, um, we have the one at the 9.5%, 97.5 percentile, which is 1.96. So the lower confidence interval is 300 minus 1.96 times the standard error, which is 16.6, or 16.16. And it's similar for the upper limit, the upper confidence limit. So what we have here is 300 um, with a confidence interval, the 95% confidence interval that goes from 268 grams to 332 grams. You would notice that the 95% confidence interval does not include zero. This means the difference between the birth weights of children from mothers in group A and group B is statistically significantly different at the 5% level, right? So your final exercise would be to change the mean estimates of group B to 3,225 grams, maintaining everything else in the table constant. Calculate the new mean difference and the 95% confidence interval, and draw your conclusions from what you found, right? So if you've made it this far and you've understood all the concepts that we've been talking about, congratulations, you're ready to do research. So what I would advise you to start doing immediately would be to download R and R Studio. The new name for them, it's actually called Posit, but you could still type in R and R Studio and have them installed on your computer. So in week 5, we'll be doing mostly practical sessions, and we'll be using R and R Studio for these. R Studio is not the friendliest of softwares, I would say. However, it's one of the most versatile that's out there, and it's completely free. So we won't have to worry about licenses. And they produce very good publication quality graphs. So knowing how to use the software is ideal for any researcher. So in terms of the practical sessions, we'll be covering quantitative summaries, graphical summaries, chi-square testing, t-testing including pair t-testing, correlation, and regression. And for the regression part, we would cover simple linear regression, maybe adjusting for a few confounders, and simple logistic regression, also adjusting for a few confounders. In terms of reference, for this course, I would recommend, if you can download Essential Medical Statistics by Kirkwood and Stern. It's actually a very handy book. And some of these concepts that we've been discussing now, they've been explained in greater detail there with great, very robust examples as well. So if you can, please download an online copy of the book. And if you find any topic a bit difficult to comprehend or follow, you can also read the book as well. Once we meet, if we meet, or have an interactive session, you could ask questions from the book or from the course as well. Okay. Thank you all for listening, and good luck.